we're going to do trigonometric functions, a right triangle approach. This is the beginning of chapter 6. We're going to take a look at angle measure. Also angles in standard position, the length of a circular arc, the area of a circular sector, and circular motion. So the length and the area, areas of this chapter or of this section was something that you probably went over back in geometry, so it might seem to be familiar to you as well. Angle will consist of two rays with a common vertex. That is your standard definition of an angle. We interpret the angle as a rotation of the ray R1 onto R2 with the initial side and the terminal side. So you can see in figure 1 we have the positive angle and then we have a negative angle. So the positive and negative are once again directional. So again, R1 is called the initial side, R2 called the terminal side. If the rotation is counterclockwise, the angle is considered positive. If the rotation is clockwise, the angle is considered negative. The measure of an angle is the amount of rotation about the vertex required to move R1 onto R2. Intuitively, this is how much the angle opens. One unit of measure for angles is the degree. An angle of measure 1 degree is formed by rotating the initial side 1/360 of a complete revolution. In calculus and other branches of mathematics, a more natural method of measuring angles is used, and that's the radian measure. If a circle of the radius 1 is drawn with a vertex of the angle at the center, then the measure of this angle in radians, which is abbreviated RAD, is the length of the arc that subtends the angle. So the bold area here on the circle is your radian measure. This is what we're describing when we give radians. The circumference of a circle of a radius of 1 is 2 pi. So a complete revolution has a measure of 2 pi radian. A straight angle has a measure of pi radian, and a right angle has a measure of pi over 2 radian. An angle that is subtended by an arc of the length 2 along the unit circle has a radian of 2. So remember, this is just a reminder that the number pi is that. It's just a number. So you can have a radian of the measurement of 1, like this first one here. You could have the measure of radian pi. You could have measure of radian pi over 2, or you could have a radian of measure 2. It doesn't have to have pi in it. Okay, so this first and second one do not have pi in it. So it doesn't have to have pi in it. You have to remember that pi is just a number. Now we looked at this already when we looked at the unit circle. So 180 is equal to pi radians. So to find a radian, you would multiply by 180 over pi. That's your conversion. And to find 1 degree, you would multiply by pi over 180. So to convert degrees to radians, we multiply by pi over 180. To convert radians to degrees, we multiply by 180 over pi. So we did take a look at this already in chapter 5, and it seemed like most of you were comfortable with this. But if you have any further questions, you know you can always ask. So let's express 60 degrees in radians, and then let's express pi over 6 radians in degrees. So to express 60 degrees in radians, you're going to multiply by pi over 180. when you do that, 60 will reduce once over 180, which is 3. So then the radians are just 1/3 pi, or pi over 3. When I take pi over 6 radians and I multiply it by 180 over pi, notice when I am taking radians to degrees, I many times will have my pi's reducing, and then I can reduce this way as well, and 6 will go into 18 3 times, so 6 will go into 180 30 times. A note on terminology. So what they want to remind you that we often use a phrase such as a 30-degree angle to mean an angle whose measure is 30 degrees. And for an angle of theta, we write theta equals 30 degrees, or theta equals pi over 6 to mean the measure of theta is 30 degrees, or pi over 6 radians. So that when there's not a unit given, the angle is assumed to be measured in radians. Let's take a look at standard position. An angle in standard position is if it is drawn in the XY plane with a vertex at the origin. So we have the vertex here at the origin, and then its initial side is the positive x-axis. Here's some examples. So we have this one. We have starting here and going backwards. We have starting here and maybe rotating around 360 degrees and then some. Or we might start here and we might go around 360 degrees and then some this way. So these are all angles said to be in standard position when you're measuring them from the positive x-axis. So angles that are coterminal with the angle of 30 degrees in standard position, and angles that are coterminal with the angle pi over 3 in standard position. So let's take a look at that. To find positive angles that are coterminal, we add any multiples of 360. So every time we go around 360 degrees more, then we have another angle, but it will end up in the same location. So 30 degrees plus 360 is 390 degrees, and then 300 plus 720 is 750 degrees. These angles will end up being in the same location, but they rotate around the 360 degrees x-axis, going around once and then some, or twice and then some. You could also go backwards, so I could subtract 360 degrees or subtract 720, so those are coterminal with theta. So again, taking a look at figure 6, you can see here we have starting at the positive x-axis, or maybe we will start at the positive x-axis and go 360 degrees and then 30 more. Or maybe we'll start at the positive x-axis and then go backwards 330 degrees. All of these end up being in the same location. To find any positive angles that are coterminal with theta, we can add multiples of 2 pi. So every time we add 2 pi or subtract 2 pi, we are going around the x-axis that amount of time. So here we have pi over 3 plus 2 pi. Here we have pi over 3 plus 4 pi. So they are coterminal with pi over 3. To find negative angles that are coterminal, we subtract any multiples of 2 pi. So here we have adding 2 pi, adding 4 pi. And again, if we're going to subtract 2 pi, then we'll end up with negative 5/3 over on this third one. Now we're going to take a look at some geometry things. So we have the length of a circular arc. So you probably learned this back in high school. And if we want to find the length of a circular arc that subtends a central angle of theta radians, we're going to have S equals the radian, or the radius, times theta. So solving for theta, we will get theta equals S over R. And we can see here that we're going to take a look at this length of a circular arc. And again, we're looking at this bold area that we have on the circle. Find the length of an arc of a circle with a radius of 10 that subtends a central angle of 30 degrees. Find the central angle theta in a circle of a radius 4 meters that's subtended by an arc length of 6 meters, and find the measure of theta in radians. So from example 1b, we see that 30 degrees we know is pi over 6 radians, so the length of the arc would be 10, which is the radius, times that pi over 6, and we'll reduce it to get 5 pi over 3. So by the formula, theta equals S over R, we have 6 over 4, so you're going to have 3 over 2 radians for part B. Now, if we look at the area of a circular sector, again, we looked at this back in geometry in high school. We have 1/2 radius squared times theta. If we want to find the area of a sector of a circle with a central angle of 60 degrees and a radius of the circle is 3, we know that 60 degrees is pi over 3 radians. So we're going to take 1/2 3 squared times that pi over 3, and we will get 3 pi over 2 meters squared. Now, circular motion is one that you probably looked at in science. You have 2 points that move along the circle in figure 12. There are 2 ways to describe this motion of the point: linear speed and angular speed. Linear speed is the rate at which distance travel is changing. So linear speed is the distance traveled divided by the time. Angular speed is the rate at which a central angle is changing. So the angular speed is the number of radians of this angle changes divided by the time. So you can see the only difference that we have in these two formulas is whether or not you're going to have your theta divided by time or your distance traveled divided by your time. So if you have a boy rotating a stone in a 3-foot-long sling at the rate of 15 revolutions every 10 seconds, find the angular and linear velocities of the stone. So in 10 seconds, the angle theta changes by 15 times 2 pi equals 30 radians. So the angular speed of the stone is theta over t, which then reduces to 30 pi radians over 10 seconds, and you will get 3 pi radians per second. Now, this unit is very important because this is your unit of measure, just like your slope. It's a rate. The distance traveled by the stone is going to be 15 times 2 pi r, so that will be 90 pi feet. So the linear speed of the stone then will be your 90 pi feet divided by 10, which is 9 feet per second. And again, this is your rate. So you want to be careful that you understand what your unit of measurement is here. Now the relationship between angular and linear speed, if a point moves along a circle of the radius r, speed w, then its linear speed v is given by v equals r times w. So if you have a woman riding a bicycle whose wheels are 26 inches in diameter, if the wheels rotate 125 revolutions per minute, find the speed at which she's traveling in miles per hour. We're going to take that 2 pi times that 125 revolutions, so that'll be 250 pi radians per minute. Since the wheel has a radius of 13 inches, half the diameter, the linear speed would be 13 times 250 pi, which is 10,210 and 2/10 inches per minute. Since there are 12 inches in a foot and 5,280 feet per mile and 60 minutes per hour, here is your conversion from inches per minute and feet, and we want to end up having our miles per hour. So we're going to get 9.7 miles per hour. Okay, well that is it for section 6.1. I'll be talking with you soon about section 6.2.